McLemore is the principal senior economic geologist with the New Mexico Bureau of Geology and Mineral Resources, a research division of the New Mexico Institute of Mining and Technology. She holds a BS in the geology and geophysics and a master in geology from New Mexico Institute and Technology, and received his PhD in geoscience from the University of the Texas at the El Poso in 1993. Currently, she is the faculty advisor for the AIPG student chapters and multiple organizations. She also is the editor-in-chief of the Mining, Metallurgy, and Exploration SME journals. So without further introduction, I give the time to Dr.
Thank you. So I'm going to kind of take a piece of what Steve just talked about. Part of that happened very quickly when this initiative came about is that the USGS started asking some of the states if they were in a position to where they could start working on this. And so there was a little piece of money that they gave us to take a look at rare earth deposits in New Mexico. And I'm just going to talk about a little piece of it, and that is rare earth elements in Proterozoic Peralkaline igneous rocks. It's at Pajarito Mountain, and Pegmatites, also in this state. I'd like to give a lot of acknowledgments to my many colleagues that have contributed to this over the years, and some of the current students. And these students, a couple of them are here in the room, they actually have been funded by this program that came out of this initiative. And this talk is certainly funded by part of that. So as we know, to kind of give a little bit more of a background, in 2017, President Trump signed an executive order that required the Departments of Interior and Defense to develop a list of critical minerals. And in May of 2018, that list was finally published. And I think it's important to understand what critical minerals are, because one of the biggest things when we start talking about it to our public is that they say, hey, copper and gold are critical minerals. Well, not under the definition. The definition of critical minerals is that a mineral has to be identified as a non-fuel mineral, and yeah, we already have an exception to that, or mineral material essential to the economic and national security of the United States. It has to be from a supply chain that is vulnerable to disruption, and it has to serve an essential function in the manufacturing of a product, the absence of which would have substantial consequences for the U.S. economy or national security. So this is the definition that the agencies have come up with. This is the definition we're working on what critical minerals are. And unfortunately, I mean, copper doesn't fit these criteria, but there are very many other important commodities that do. There are 35 critical minerals that were identified, or groups of minerals, and New Mexico has a number of these. I kind of like to put it into a periodic table. I think all of us in this room can understand that, and if I can, whoops, yeah, I did something. Okay, here we go. Okay, I'm trying to find the, yeah, okay, so what I've done here is just in terms of New Mexico, all of these minerals that are shaded are critical minerals, and I've identified in red the ones that are currently producing in New Mexico, and we are producing helium, so I do have to fix that. The ones in blue are elements that were once produced from New Mexico, and the green are elements that are found in New Mexico, and the yellow ones are ones that we don't know that we really have in New Mexico, although I think we may actually find out some of them do occur in one form or another. And so I'm only going to talk about a few of the rare earths today. And rare earths, as you all know, you pick up your laptops, you pick up most anything electronic today, including your solar panels, your green energies, your wind turbines, and they require rare earth elements. And they require a fair amount of them in terms of production. So this is a map of where we find occurrences of rare earths in New Mexico. Now remember, I'm from a state survey, so I am limited to the state that I live in, that the people are paying for me. And so what I'm going to talk about today are the ones that are, these districts that are shown here in yellow. These are the ones that are Precambrian. There are other deposits. There are other deposits that probably have more potential, but I just chose for this presentation to choose those. And one reason that I chose those is that now the Igneous Mountains are up here in Lincoln County, and we actually do have another contract to do some of the MRI work, the mapping, and some of the geophysics will be done in this, because this is one of our better districts with vein type of rare earth elements. But it's tertiary in age, so that's all you're going to hear about me from on that one today. But I guarantee you next year you will hear some more. But the thing is that in the past, a couple of these pegmatite districts that are mostly up here, although there is some down here in the southern part of New Mexico, they had a little bit of production of rare earth elements. So that's the first place you want to start. We are doing the beginning part of mineral resource assessments. And the first one that I do want to talk about, we did not produce, but it is, in a lot of people's eyes, one of the predominant rare earth or potential predominant rare earth deposits in New Mexico. And this is at Pajarito Mountain. It's down here in Otero County. It is on the Mescalero Indian Reservation. There has been some work done in the past. This is a geologic map. It is a nepheline cyanide complex. And these are rare earth element patterns. A lot of this is from a thesis that came out. What I've shown here in this particular diagram is where some drilling had occurred about 4 years ago, and then a master's student at Colorado School of Mines did the work on this core as his thesis. And all I've done is taken the work that we've done in the past, the USGS has done in the past, that companies done in the past, and combined it with what the student has done. And what is interesting is that this is 100,000, this is the sample rare earth to rare earth chondrite, so it's normally the way we look at rare earths. These are the rare earths, so it's not exactly parts per million, but it does give you the idea of the rare earth patterns. And it's a fairly flat pattern. This is 10,000 parts per million. And what is important about this and why this deposit is in everybody's spotlight, so to speak, is that this has elevated heavy rare earths, which are important for a lot of the components that we are looking at. Mineralogy, right now it's eudialyte, which is, these aren't rare earth minerals. Eudialyte, fluorite, apatite, zircon, all of these are carrying some rare earths. This, Mike Berger found this out in his thesis. And then in addition, there is 2 rare earth bearing silicate minerals that he could not identify. So we definitely need to do a tremendous amount more work on this deposit if the Mescalero Reservation is interested. In 1990, to give you an idea of where this deposit could sit, in 1990, Molycorp reported in a historic. These are not 43101, but they still give us an idea of the deposit of what the company thought at the time. And they were looking at 2.7 million short tons of 0.18 yttrium, which is one of the rare earths, and 1.2% zirconium. And this was predominantly in eudialyte. And then further along, on the historic rare earth resource was developed of 537,000 short tons of almost 3% total rare earths. Now, I think these are very conservative, but at the same time, we've got to take modern resource reserve estimates and criteria and really figure out what is there. If we were to plot this on a grade tonnage of selected rare earth deposits, Pajarito Mountain would fall right in the middle of all these. Galena's just the Igneous Mountains is just a little bit further up in this scale. And so these deposits could very well rank with a lot of the others that we're looking at, but it's grassroots. There's been very little work done on it. I now want to focus on some of the granitic rocks that we have, because I think, once again, this is the purpose of this part of the funding that we're getting, is to try to identify some of these areas that eventually need to be looked at. You've got to have deposits in the pipeline if you're going to have a sustainable supply of rare earths. And so we turn to some of the Proterozoic granites. This is one of them up in Taos County, up around in here. This is La Cueva district. It was looked at originally for uranium, but once again, there are hints of rare earth component, And in fact, some of the analyses you can see here are almost 2,000 parts per million cerium and 600 parts per million lanthanum. And that's just uranium, based on uranium samples collected for uranium. These granitic rocks are subalkaline, metaluminous to paraluminous. No drilling's been done there. This is the mineralogy from another thesis. These older theses are critical, and part of our project is to try to get these theses scanned so that they're available for industry to use. They are an excellent source to get started in this business. The Tahoe granite in Chupadera District in Socorro County, I actually have not, this is a new district that we found, and it's right about here. And once again, this was a map that I did back in the 1980s looking at uranium. A company came in, they did do that drilling. We have that drill core there in Socorro at the Bureau of Geology. I have a couple of my undergraduate students supervised by one of our graduate students, who better be in this audience here. And they're looking at relogging this core. We're going to sample it, and we're going to try to see if indeed this granite has any potential for rare earth elements. We do have one analysis that indicates that perhaps it's, like 1,200 parts per million yttrium. This is what the granite looks like. Uranophane, if you can really good, you can see some of the yellow uranophane on some of this core. I wanted to spend a little bit of time on pegmatites because that is where the production has occurred in the past. Before I go to pegmatites, there are a couple of other Proterozoic granites that we do hope that we can take a look at, and we've identified it when we started doing this data preservation project. The pegmatites, pegmatites are coarse-grained igneous rocks with lenses, veins. They're generally granitic composition. They contain essential quartz, feldspar. They represent the last and the most hydrous phase of the magma. This is a view here. Let me see. This one is for one of the Pataca districts, and a lot of this is monazite, which is a lot of the common of the rare earth minerals. These are predominantly these yellow districts, and then down here in the Burro Mountains. Most all of our pegmatites are Proterozoic in age. Just some other views of some of the pegmatites. They were looked at for a variety of things. They actually, a number of them produced beryl. At one time, the Harding pegmatite, which is withdrawn from mineral entry, was the U.S. leading producer of beryl. It was leading producer of feldspar. It was leading producer of lithium, right in here. So these pegmatites in the past have produced a fair amount, and were substantial at that time. And a lot of these are critical minerals. The Harding is a laboratory that is owned by the University of New Mexico, so it's there for us to go and study and to understand pegmatites. So that one won't be mined. It's interesting, the rare earth to chondrite patterns, they're just all over the map for these pegmatites. And this was done by, in the late 80s by our AA work, atomic absorption. So it's not the best way to do analyses. We're hoping that we can get some funding, that we can actually go back and understand the mineralogy of these pegmatites and where these critical minerals are residing, not just rare earths. Here at Elk Mountain, we've got this zone of muscovite, and that a lot of times is where some of these rare earths and other critical minerals tend to hide out. These are some of the minerals. Sorry I didn't put the formulas up. They're not all rare earth minerals per se, but they do contain some of the rare earths. And between Pataca and Harding, we do have some pretty good idea of the mineralogy, because the mineral collectors have spent a fair amount of time on that. And there's a lot of high quality publications on that. But some of these other districts do need to be taken a look at. For example, this is one of the pegmatites in the Pataca district in the northern part of the state, and you can see that the rare earths are coming out late in the paragenesis. And so these kinds of studies need to be done in more detail at more of these types of deposits. So in summary, and this is probably a record for me, I'm finished early, but the best potential for rare earths in Proterozoic rocks in New Mexico are probably there at Pajarito Mountain, and perhaps some of the granites. but that remains to be seen. That work has to be done. As I said, we are looking at students looking at the Tahoe granite, and if we can get some funding and continue with this funding that that USGS is doing, the USGS pays for their salary, and then I just got to find money to cover their analyses. And these students are getting into it. They are excited to work on these projects. They are really excited to be up there looking at this core. My director actually went up there, and that was one of the things that impressed her. So she'll be funding some of this as well. But additional geochemical studies are needed, and ultimately, you know, the industry is going to have to do some drilling and determine if these can be deposits. They're not going to be mined in the near future. I mean, we're looking at 20 years probably, but you've got to have these deposits in the pipeline. Most of the pegmatites in New Mexico, I don't think are going to be developed for rare earths. I could be wrong when we get the studies done, but the one, you know, the Harding, it is withdrawn from mineral entry. A lot of them are in the wilderness areas, but still don't want to completely write them off. So rare earths, as I hope I've convinced you shortly, is that they are important for green technologies as well as our entire lifestyle. They're found in specific locations that are controlled by geological processes. So they're just not found everywhere, and we've got to have this other component that Steve talked about as to land accessibility for the exploration geologists to get out there and find these deposits. And some of these are required for the very lifestyle that we're looking at and that we hope that our grandkids continue. And we've got to understand these geological processes, and we start that by just understanding the mineralogy and chemistry, the distribution of these minerals in these known deposits. I am, as you heard, the exploration editor-in-chief for our new journal, Mining, Metallurgy, and Exploration. We had a special issue last October and February that came out on critical minerals. If I can get together about 8 more papers, I can have another special issue on critical minerals this year or even next year. So I'm hoping that some of the authors that follow me will be interested. I know I have at least one paper that got stalled in the USGS publication process that could contribute to this. I also need some editors, and we are not limited to critical minerals. I need articles on geology, industrial minerals in general. So I'd like to end this. I know you can't really see him, but not only do I teach college students, but down here is my, he's now 12-year-old grandson. And, you know, this is one of the hot air balloons. You could say it was helium, but it's really hot air balloons. And this is what we're all trying to do. We're trying to make sure that our grandchildren and these young guys that are coming after us have the same kind of opportunities and the same kind of lifestyle that we have. And it's going to require these critical minerals, and it's going to require the kind of work that we're doing. And training of that workforce is essential. So with that, I think I've got 2 minutes to take questions. Thank you. Yeah, Paul. I'm sorry. That's his brother. Dave.
Question on that. How do these deposits stack up grade-wise, say, to the Chinese deposits? Do you know?
Well, yeah, because I have on that diagram. Mountain Pass is, I'm trying to translate, Mountain Pass is up here, and the best estimates that we have for bionoble carbonatites are here. So most of the rare earths right now are coming from carbonatites, and that's where I have spent a lot of work and also have published a lot of things. And this time I thought I'd talk about the Precambrian. So here you're looking at, and that's what I've gotten. This is, you know, these are the carbonatites. The dark purple are the alkalic igneous rocks, these granites I've been talking about. The green are the iron oxide copper gold deposits. The light purple are other igneous related deposits, and then the yellow are metamorphic deposits. And so those are some of the great tonnages that we have out there, and you can see the sources. Yeah, well, I'm going to say something that a lot of my geology colleagues won't like, but the metallurgists were, is that you know, we study grade, we present grades, but we really mine minerals, and it's the metallurgists that have to know what the minerals are. And so the carbonatites generally have minerals that come out together that have all the rare earths, whereas if you go to these granitic and alkaline rocks, a lot of them are in a whole bunch of different minerals, and they're harder to get all the rare earths out. So that's where it becomes really important to yeah, you got to think grade because that's what the investor is and that's the model we have, but you got to get it down to minerals. And what is the mineralogy? Where are these minerals? And right now the technology for carbonatites is great. But I also will add, I know I've got some friends of mine here in the uranium industry. Elliott Lake up in Canada at one time had a cerium circuit. They were producing rare earths from their uranium ores. And so I can see that as a possibility if we do ever get a uranium industry developed again in this country, that we could. I mean, some of my preliminary data is showing about 300 to 500 parts per million rare earths in some of these uranium deposits. So that could be lucrative to go after. And we're looking at a lot of other, the rare earths we're going to see, I think, some of our biggest advances because we're so far along in them. But the other critical minerals are just as important. Yes?
I want to compliment you on your presentation and the potential, but especially of the 20 to 30 papers given on rare earths at this conference, yours is the only one in preprint.
Thank you. I'm sorry to see that, but hopefully we can get a lot more of them into the journal, or even mining engineering. If you all look at the mining engineering, I have a critical minerals paper that I did last year that's in the issue of mining engineering that you have. And that, I'm glad you bring that point up. We've got to get this information out. Yep.
Just want to follow up with that. Does the SEG even know that this exists?
They should, but you know, they're a different focus than what, yeah. And that's where I'm hoping that our journal, the SME journal, helps to fill that gap, and that we can get more of these kinds of papers into our journal. And so all we can do is just work towards that.
I know your talk was focused specifically on New Mexico, but these Proterozoic Igneous rocks and the developed rocks that stretches all the way across.
Bingo!
What do you think the exploration potential for rare earth deposits in these alkaline rocks and other places?
Yeah, it really gets down to building our economic geology programs at the state surveys with the USGS and at our universities so that we can have those folks going out and doing the kind of work that I'm doing. I'm lucky. I didn't get fired. I'm the last of the economic geologists at the Bureau, and we are now building up our program. We have a new economic geologist coming in. And so that's what's going to address that. The only reason I can talk about New Mexico is because those other states did not have the capacity to do that. Some of this funding from the USGS MRI and the database preservation hopefully will fill some of that gap, and I think we will start seeing more and more coming out of the state surveys and then in turn from the universities. So yes, I think there is potential, and there's probably better potential elsewhere.
And then is there much industry support for this type of research?
So Freeport has given me a little bit of a donation to have some of these students work on some of this, but the answer is no, not yet. My funding, I got a little bit of a donation from Freeport, I got a little donation from one of my former students, and the rest of it, it's the Bureau, it's the taxpayers of New Mexico, and then these two programs from the USGS. And we would love to have some industry, because, you know, the one project I have that's paying for most of these students is only $35,000. And even the mapping program, we're only looking at $125,000, and I've got to supplement all of that. And these are the kinds of grants that the survey is giving out to the state surveys to be doing this kind of work. So if we can get some industry dollars and some industry focus, and I think industry is definitely involved in some of the other deposits. So, but I'm in New Mexico, so. Okay, well, thank you very much.
Okay, our next speaker is Dr. Tom Lograsso. Dr. Lograsso serves as the Deputy Director of the Ames Laboratory, where he is actively involved in the program development, oversight of the environmental safety and health, and the space management. He currently serves as the single crystal preparation group leaders and continue to focus on the group research activities on developing the synthesized protocols for materials containing the volatile, toxic, and reactive components. And I think he is also developing the substitute focus area leader of the CMI, which is the DOE Energy Innovation Hubs.
Thank you for the introduction, and thank you for allowing me to come and talk about the efforts of the Critical Materials Institute. That introduction's a bit old. When I submitted the, if you could, thank you. When I submitted the abstract, I was the developing substitute focus area lead for the CMI. Since that time, I'm now serving as the interim director for the Critical Materials Institute. So, taking a little bit of speaker privilege, I've expanded my talk a little bit to talk about the Critical Materials Institute as a whole, and then focus in on what we're doing in the area of permanent magnets, and in particular the rare earth critical materials. So I kept my title just to make sure people walking in says, yeah, this is the talk I want to be at. But let me go ahead and proceed. So the Critical Materials Institute is actually a Department of Energy Innovation Hub. It was established in 2013, so we are in our 7th year of a 10-year appropriation. The work that we do really goes to the first action item that Steve mentioned, and that's advanced transformative research. The Institute has a portfolio of 35 projects covering actually a pretty broad scope across the supply chain. We've been fairly successful, over 120 plus inventions over the 7 years, 12 licenses that came out of that. We're a network of about 25 different team partners, 4 national laboratories, 9 universities, and 12 industry partners. And we follow the strategy of the DOE when addressing critical materials, diversifying supply, developing substitutes, and reuse and recycling. And if you recall from Steve's slide, that was on the sidebar. Those were the 3 strategies. Overall, we have about 300 researchers across all those institutions. Industry cost shares about 25% of the effort that we are utilizing. We engage them early. As you'll see from our mission, we engage them early because having industry providing the guidance allows us to accelerate the development of the technology. So our mission is to accelerate the development of technological options that assure supply chains of materials essential to clean energy technologies. And I think that's important. The response to the executive order identified 35 materials. No one program can address all 35 critical minerals. We use a filter of clean energy technology. The office that supports us is the Advanced Manufacturing Office. And so the clean energy technologies that we utilize or focus our attention on are electrical generation, so wind generators, which use up to 2 tons of neodymium magnets, electric mobility, electric drives, traction motors, high-efficiency motors for electric vehicles, as well as energy storage, lithium-ion batteries. We also, at the onset, looked at lighting technologies. Fluorescent lights utilize europium and terbium, and it was one of our successes. In the first 5 years, we developed a rare earth-free red phosphor, as well as a green phosphor that had 90% less terbium. Those went into manufacturing trials. The industry partner was there from the beginning, and that helped us develop a material and basically have it reach manufacturing trials within 3 to 5 years. The challenges we face as an institute, we continue to work on the methodology to anticipate criticality. We always want to be looking forward, anticipating. When crises happen, they happen quickly, and we want to be able to anticipate those and have options on the table so that we have the ability to react. Over the years, we've come to realize that recovering or using critical materials from unconventional or dilute sources is really an important aspect. Many of the critical minerals on the list are byproducts. They are not primary productions, and as a result, certain, let me say, techno-economic factors come into play. We want to accelerate materials discovery. We go well beyond the materials genome project, where that tends to focus on predictions of intrinsic properties. We tend to take that as a starting point and then begin to add on other selection criteria from the manufacturing sector. For example, in the lighting industry, the intrinsic properties yielded over 500 different compounds. Our manufacturer came in and pretty much got that down to 3, based on the fact that phosphors have to be water compatible. They have to not degrade in mercury vapor. They had quick, accelerated tests, and we could quickly zero in. And then finally, the last strategy is to drive reuse and recycling. Clearly, if we don't have enough of any given material, we want to be wise in how we use it or reuse it. Okay, so as I mentioned, the scope of the Critical Materials Institute really addresses the needs of the entire supply chain, with one exception on the two extremes being out of scope. So mining and concentration, or mining and exploration, we do not do. That is the domain of the USGS and others. It is at that point, once we have an ore to process, the extraction and refining on through the various steps of the supply chain up to really part manufacturing and sometimes sub-assembly manufacturing is where the Critical Materials Institute attempts to address the needs of the supply chain. On the outside, sub-assembly manufacturing, system integration, that really transitions over to other parts of DOE applied office programs, like the Vehicle Technology Program, where they're actually assembling motors, and maybe they can utilize some of our new magnets, but their focus is on really the sub-assembly manufacturing and system integrations. So in terms of diversifying supply strategy, we focus in on efficient separations and improved concentrating and concentration techniques. And finally, environmentally safe metal conversion. If you're familiar with the rare earth process, once you get the oxides separated and concentrated, converting them to metal can be quite environmentally difficult. With emissions of fluorine and other contaminants. Developing substitutes, we look to develop new advanced materials, and right now our focus is on permanent magnet materials. We do developing substitutes. We can substitute a material for a material or an element for an element. We can also substitute a process for a process. And finally, we can substitute a system or a component for a component. That latter part is out of scope for us, but anytime you develop an advanced material, hand in hand comes the processing, and if we can develop a better, more efficient or energy efficient process for an existing material or our new materials, that falls into our scope. And finally, driving reuse and recycling. We obviously are looking for energy efficient and cost effective methods, and we're trying to utilize circular economy principles. Tying this all together is our cross-cutting tools. Again, these are both scientific and technological tools, but also we look at environmental factors of the processes and the technology we're developing, as well as criticality assessments, life cycle analysis, techno-economic analysis to make sure that the solutions we have are viable solutions. Okay, so as I think I mentioned, we're focused on permanent magnets. That's really the rare earth elements, in particular dysprosium and neodymium. Energy storage, lithium, cobalt, and carbon, and electronics, gallium and indium. So I think what I want to do is just focus in on permanent magnets as I originally intended to. So when we look at the current market for permanent magnets, there's a rather limited palette to choose from. We really have two choices for mass market. That is sintered neodymium iron boron over on the right. It has the highest energy product, likely the best performance for most applications. And on the other end of the mass market are ferrites. And those ferrites, actually, there are more ferrite magnets by weight than neodymium irons produced. They are the cheapest. Clearly, neodymium iron boron brings the value, so we focus a lot on the neodymium iron boron. It's that high performance of those magnets that allow us to miniaturize everything, from our phones to our cars. We get weight savings, and clearly those centered magnets are important. There are other magnets that are used in more of niche applications. Samarium cobalt is a high temperature rare earth magnet. It actually rivals neodymium iron boron in applications where, for instance, aerospace applications where the temperature range is needed. Bonded neodymium iron magnets and alnico, aluminum, nickel, cobalt, and iron based magnets are relatively low performance magnets. So if I'm designing a system and I want to use, or I have a need for a magnet, and it's a mass market, I have two choices. I could go with the ferrite and go low performance. What that means is my motor will be less efficient, it'll be larger, or I can go with neodymium iron boron. There's nothing in between. So there are two opportunities when we look to develop a substitute. One is obviously to get something as good or even better than neodymium iron boron. That's a tall order. Neodymium iron boron has been around for 40 years. Lots of work has been done. There are some new formulations, I'll talk about that. But it's this region in between neodymium iron boron and ferrite where, you know, for a given application, if I want a high efficient motor, I may not need all the performance that is presented by neodymium iron boron. Right now I don't have a choice. I have to use it. If we can develop a gap magnet or a magnet that fits in this gap, then I reduce the demand on the neodymium. And in doing so, I reduce criticality. So I'm going to do 4 separate highlights here of some of the work that we've been doing. And I kind of wanted to do that in the context of permanent magnets, but I want to also kind of do it in the context of supply chain. So along the left, I have the supply chain, and I just want to highlight some of the things that the Critical Materials Institute has done to improve processing at various stages. So my first example is more efficient leaching. This is leaching from basanite ore, so it's a rare earth ore. The ore is about 75% lanthanum and cerium. Neodymium's down around 8%. Typically, the current practice is a hydrochloric leaching process. That leaching and cracking process, that process currently yields about 50-55% yield. We've been able to develop a one-step leach that combines a couple steps, so it's more of a one-step process that eliminates the caustic crack step. In doing so, we're able to bump that efficiency of separation up to 90% recovery. In doing so, we reduce complex processing and chemicals and labor, so OPEX costs are lowered as well as CAPEX, and the process allows the hydrochloric acid to be recycled. Moving down the supply chain then, it's one thing to get the oxides. We have to convert it to metal. We're going to make a magnet. This team's efforts resulted in developing the ability to monitor the electrical conductivity in an electro-refining cell, and in doing so was able to monitor and control the process much better. As a result, they could reduce the amount of energy used by a third to 60 or 70%, with that additional process control, they didn't have to overdrive the cell and therefore avoided the emission of organofluorine. So in this step, we're able to produce a more green approach to the standard electrolysis system. Okay, so now we've got our metal. We can make magnets. As I mentioned, basanite really is a lanthanum and cerium ore. So the more we can use lanthanum and cerium in our magnet formulations, the better off we are. If we're going to dig up the ore anyway, the lanthanum or the cerium is going to come along. In this formulation that was first predicted using theory, we replaced half the neodymium with lanthanum. And that naturally reduces the magnetic properties. So we add cobalt to boost it back up. Yes, cobalt is a critical material, but we have to do something to compensate. So basically, instead of neodymium-2, iron-14 boron, our formulation is lanthanum, neodymium, iron-12, cobalt-2 boron. The Curie point is higher because of the addition of the cobalt. And as a result, although the magnetic performance of this new formulation is less at room temperature, it retains those properties to higher temperatures. If we did not, or if you do not have that capability, what you have to do is add dysprosium to the mix. Even in the pure neodymium iron boron, to get to higher temperatures, you add dysprosium. So this formulation avoids the addition of dysprosium or reduces the amount of dysprosium needed, but furthermore, it replaces half the neodymium. So in a simple way of thinking, if you dug up a kilogram of ore, you should be able to get twice as many magnets from that same kilogram of ore. Maybe it's a little naive, but the potential is there. Finally, using cerium as, again, another use of cerium, we can develop a magnet that fits into that gap region. And in doing so, what we base this off of is cerium cobalt 5. That's similar to the samarium cobalt formulation, but now we replace the samarium with cerium, obviously much more abundant. And it's been rather remarkable. We do add a little copper and a little bit of iron to adjust the chemistry. And in doing so, we actually adjust the microstructure of the magnet. And what's remarkable is in the as-cast form, we get these wonderful hysteresis curves, which is the upper diagram, that are really square in shape. And the squareness of those curves is what defines a really good magnet. And so while the performance is only 13 to 15 megagauss Oersteds, neodymium can be on average around 40, peaks out at 55, so it's only a third, but it falls right in that middle of that gap. And so we anticipate being able to utilize this for a number of different applications and where there'd be no other choice for neodymium. Cobalt is a critical material. We've done a lot of work trying to substitute for that cobalt by adding the iron, and we've been able to reduce the cobalt content from 68% by weight down to 48%. So it's all kind of, working together, we've developed a fairly decent gap magnet. We've coined the term gap magnet. So that's where we're at, and I think, finally, if you don't have enough of a material, then you want to use it wisely. One way to do that is near net shape processing and, in particular, additive manufacturing. And we've been able to not just print magnets, but we've been able to print the housings and really develop a fully working, all additively manufactured brushless DC motor using isotropic neodymium iron boron. So this is just commercially available neodymium iron boron, but what we have avoided is all the manufacturing waste. Generally neodymium comes in blocks or is fabricated in blocks, and then you cut the shapes, and in doing so you can lose 40 to 60% just by your slicing and dicing, depending on the size of the magnet. So this is an alternative. It's actually got the industry a little bit excited because not only can you do near net shapes, you can do shapes that you wouldn't normally be able to cast. So you can match it to your motor, match your motor design, and fabricate the magnet in the shape and size that you need. Okay, so to summarize, I guess, if the Critical Materials Institute really has established a framework that couples research using our strategies of diversifying supply, developing substitutes, and driving reuse and recycling with early industrial input on issues and challenges that they see and face in terms of adoption, criticality assessments, road mapping, techno-economic analysis, life cycle analyses, and supply chain analyses that allow us to accelerate the development of technological options. And those are all our partners, and I entertain any questions.
Quick question, are the development of these new magnets, is this based upon some kind of quantum mechanical modeling, or is this being done by trial and error?
So the computational approaches use density functional theory to develop the intrinsic properties. We also have magnetomechanical modeling to develop hysteresis curves, and then ultimately finite element modeling to guide us as to what application space a particular magnet might have applicability. That is all followed up or coupled with experimental determinations. So no, we do a lot of screening and predictions through those computations. We have an AI and ML machine learning effort on existing databases of magnetic properties. Interestingly, not to necessarily find the materials that are, say, in between known materials, but there are many materials that should be magnetic and aren't. And, right, they contain enough cobalt, but for some reason, maybe they're paramagnetic. And we've been able to identify those and then manipulate them chemically to make them ferromagnetic. So we'll expand that to the iron base, kind of maybe three rules, three friends in the magnet industry. One is lanthanum, cerium, because those are the most common rare earths, and iron. Iron is your friend. That's what I've been told. Iron is our friend. It's got good magnetic properties. It's relatively inexpensive. It is inexpensive. And so the more we can move toward, stay with iron-based formulations, the better off we are. So it's a good combination of both modeling and experimental.
Any questions? Any further discussion? Thank you very much.
Okay,
Yes,
thank you.
Hello, everybody. Good afternoon. The topic of my presentation is about space mining, as you can see. This is the agenda that I'm going to follow, basically. And as you know, our solar system is full of critical raw materials. Asteroids such as Davida, for example, have mineral resources that worth about 27 quintillion US dollars. And their exploitation could be a sustainable solution for mankind and also for the end of the dependence of free resources on Earth. But before going deeper on this question, I think we should ask to ourselves who will be the owner of these valuable resources. Should the universal access to be guaranteed to everybody? Do we have the technology required to develop space mining? So if we take a look at the satellite industry, we see that since 1957, that the first satellite was launched, till now, there are more than 1,500 satellites in orbit. So which means that it's a huge number of satellites. And 63% of these satellites belongs to only to three countries, the United States, China, and Russia. So which means that it seems that there is a growing interest in not only in space mining, but also in things related to the space, probably originated because of the question if the Earth will have a sufficient capacity to meet future needs on critical raw materials. So in order to have a full understanding about this matter, I think it's important to take a look at the regulations, framework, the resources, the projects, and the technology that is required. So if we take a look at the history, we see that in 1967, the Outer Space Treaty was signed in order to avoid that any country can, I would say, claim sovereignty over any space body. And years later, but something was missing at that time, because something important, because nothing was mentioned about mineral resources. And years later, the Moon Agreement was signed in order to, but was signed only by 17 countries, and they developed an international framework, and they also agreed in the way to manage the exploitation of the mineral resources in the years later. So since then, many milestones have happened, but I would like to mention two of them that they are quite recent. In 2016, the Luxembourg government, they developed a draft law in order to assure that private companies, they can have like a legal framework for being confident about what would be their rights or not in this endeavor. And also 1 year later, they signed an agreement with the European Investment Bank in order to provide advice and financial, I would say, instruments for private companies. So if we think about resources, we see that moon mining, for example, we can find helium-3 rare earth elements, billions of tons of water ice, and that could be very useful and less risky than, for example, Mars water missions. And on the other hand, asteroid mining, for example, we can classify the asteroid in 3 types, like metallic, carbonaceous, and stony types. The most popular is the carbonaceous one. The composition is basically nickel iron, and they have a high concentration of rare earth elements and also platinum groups, comparatively with the concentration that we can find here on Earth. So related to moon mining, for example, what are the projects that nowadays are being developed? And the NASA strategic plan for lunar exploration, they expect to launch 37 moon missions from now to 2028, which means it's almost an average of 5 missions per year. Nowadays, they are working on 3 robotic spacecrafts working on lunar surface exploration. In 2024, they want to develop the Artemis program in order to launch the first, in order to land the first woman and the next man on the moon. And 4 years later, they are also working hard in order to establish a sustainable exploration on the moon surface. And there are more than 9 companies nowadays working with NASA in order to delivery services, in order to provide delivery services to the lunar surface. And NASA also committed to an investment of $2.6 billion for the next, or within the next 10 years. And they are also working in a project to develop what they call the Lunar Gateway for a small spaceship that they will be orbiting the moon and to provide a quick access to the labs, quarters, ports, etc. for astronauts. So from the European side, we have basically 2 projects. One is called ISRU, is in situ resources utilization in order to extract oxygen and water from the regolith, from the lunar regolith. And the other one is called Prospect for assessing the potential resources over the moon surface. And there are also other countries. For example, Japan is developing the project Hakuto-R in order to launch 2 missions, M1 and M2, before 2023 for lunar landing and also surface exploration and data collection. And China, for example, and India, they are more focused on helium-3 in order to meet the world current energy demands for the next 200 to 500 years. In terms of, or related to asteroid mining, we can see that since 2005 to 2010, NASA collected the first samples from the asteroid Itokawa. And by 2013, they developed, they reactivate the project called NEOWISE in order to provide more information about the composition and the size of the near-Earth objects. And from 2018 to 2023, they are working to develop the project OSIRIS-REx mission for that will be the second asteroid sample return mission from the Bennu asteroid. Japan is also working, as I mentioned before, in the mission called Hayabusa 2 for the asteroid Ryugu, that this year, hopefully, will come back to the Earth with some samples. And also there is an American company that is very interesting, that is focusing on commercial exploration and prospecting of asteroids, and they are mapping out all the asteroid resources, and they want to provide all this information for the investment community and also mining companies for them to make more accurate decisions. So here in this table, I wanted to mention basically 5 projects of 5 companies for you to have an idea about the variety of projects. For example, planetary resources, they They want to build the first commercial mine in space in order to harvest water that will be used as a rocket propellant. For example, Orbit Fab, they are working in order to develop the first gas station on orbit, and they will be operating the first operational tanking within this year, in 2020. And made in space, for example, they are also working on additive manufacturing and robotic assembling technologies. These Lunar Industries from Luxembourg, they are creating what is called the first space-based metal refinery in order to make the more sustainable and to treat the space debris and removal and recycling all the space waste. And Active Space Technologies from Portugal, they are developing and working on developing electromechanical system that can work under extreme conditions. And these systems will be used for different type of instruments, mechanism actuators, wireless systems, etc., that will be implemented in satellites and space mining robots. So, but the challenges are really multiple for developing space mining. There are different factors, for example, conflicts between international regulations, different political interests, security reasons, environmental reasons, ethical reasons, strategic, technological, economic reasons. But I would like to pay attention to three of them. For example, for the ethical and opportunity standpoint, there is a consensus that for sure the space mining is an opportunity for that will contribute to the development of all mankind. But there are also discrepancies about the access, if the access will be only reserved for developed countries or not. So from the strategical point of view, the scarcity of critical raw materials on Earth can speed up for sure the development of space mining. But on the other hand, a responsible and sustainable development plan on critical raw materials could affect this development negatively. So, and technologically speaking, the development of new technologies and substitutes here on Earth may reduce the dependence on critical raw materials. So that can also affect the development of the space mining. Here is one funny question that I asked to myself is like, is the space mining a science fiction movie or not? It's like, what kind of conclusion can we make about this? And you know, I was thinking about, for example, what's going on in the world. You know, if the universities are involved or not. And I realized that there are many programs. For example, Colorado School of Mines was the first university thinking or developing an academic degree program for space resources and in situ resource utilization. The University of New South Wales as well, and the University of Luxembourg, and worldwide there are also many other, I would say, countries that they are working on this: China, Canada, Germany. So in this sense, it seems that something is going on. And if we take a look at the big players, we see very, very, I would say, reputed and big countries and big companies involved, and also a new generation of what is called space pioneers that, for example, only in Europe, there are almost 100 companies, like I counted 98 companies that they are developing the technology that will be used in the satellites and the space mining industry. So if we summarize everything, and perhaps we can think or we can state that a new economy era has just begun. So, but in my opinion, there is a problem, a huge problem. And there is a high risk that can jeopardize the supply of critical and non-critical raw materials in the short term, and also the project development, not only of space mining, but also exploration and even mining projects. And in the long run, also can jeopardize the sustainability and the future of young generation. And that problem, in my view, is the bad image. Mining is the forbidden word. We cannot say mining because everywhere is very, very concerned about mining. So also the none in my backyard syndrome that is deeply ingrained in Europe and worldwide, and the resistance, the environmental resistance, social pressure, and organized activism against mining can also, contribute negatively to, to this problem, So in my view, what we need to do in order to fix this problem is to assure and to monitor that governments have an open-minded conversation with the public, with all the stakeholders, schools, universities, non-governmental organizations, industry, everybody. For doing what? To transmit a clear message to the society that the extractive sector is vital. It's vital for the comfort, health, and also development of well-being of the society. And this message should be spread worldwide. And at the same time, we need to work on mineral resources for sure, that they are protected and measured according to the United Nations framework classification of resources. And also we need to work on exploration and mining activities that they are properly funded and managed by all the entities that are involved. And also transparency. Transparency is vital in this sense. And we need to maintain a responsible behavior, respect the sustainable management of critical raw materials, because it's prescribed by the United Nations Sustainable Development Goals. So I would say we should do it. And also we need to work on facilitating the coexistence of extractive industry with other activities in order to make, sustainable, the development of all humans. So if we do that, the solution is easy. The solution is easy. It's only a combination of, let's say, different solutions. From one side, for example, we can be focused on boosting and promoting the sustainable underground mining as probably the most immediate and sustainable solution, but also respecting and keeping in mind all the pillars of the sustainability, the economic pillar, society pillar, and environmental pillar, and the sustainable development goals. And at the same time, working to develop open pit mining with sustainable practice on exploration and mining and social engagement, working also on recycling and on space mining in order to guarantee the universal access to resources and also safety and the technology. So if we do that, probably we can say that the space mining augurs considerable benefits for the future generations in many ways, as a source of critical raw materials for high value and also high value mineral resources, also as a palatable facilitator for boosting the development of new economy and as economic and social development of future generation. But doing that, the way is still very long. And we need to reinforce research and innovation in order to secure the safety and sustainable exploitation of space resources are guaranteed. Also to avoid that the mining aversion is exported from Earth to the space and to converting the space waste as probably the next environmental threat of humans. And also the international cooperation will be key because the mission is huge. So without international cooperation, this mission will fail, I'm pretty sure. So should be universal and not undertaken by only a small group of countries or enterprises. And sorry, wait. Okay, these are the references. And thank you so much for attending this presentation, and thank you to the SME for publishing this paper in the mining magazine, in Mining Engineering magazine. So that's all. Any question?
So where do you think we are now as far as mining space is concerned, timeline? When do you think it will happen? 30 years? 50 years?
Okay, if we pay attention to the 5 examples that I put there in that table, you would see that within this year, there will be projects that will be developed, in order to, I would say, to pave the way for further development. And if you see the schedule of the NASA, for example, they are thinking in an horizon of 8 years to have, let's say, permanent exploration on the moon surface. So it's not so far. It's not so far. But, okay, in my view, I think there is a lot of work to do. Still. You're welcome.
Sir, how would you balance using potentially easy-to-access resources in orbit and fear of depleting those resources that may enable us to get to resources that are even further away?
Could you repeat the question, because I couldn't understand you? How?
Do you understand the wording or my voice?
No, I could hear you, but I couldn't understand the question.
So it occurs to me that some resources would be easier to exploit than others.
Yes.
Their proximity to Earth and the amount of energy it would take to reach them.
Yes.
And those resources could enable you to get to resources that are much further away.
Yeah.
Not low Earth orbit, but outside of our immediate
Yes.
region of the solar system. How would you balance using those resources and avoiding depleting them so that future generations could get very far away, but we could use those near Earth resources?
Okay. In my view, I think we should analyze the problem in this way, like what kind of resources could be economically feasible to be extracted quickly, let's say, and what kind of resources can help us to achieve, I would say, more ambitious missions like later, because in my opinion, the possibilities of the space mining are huge. I think probably more than we can understand with the information that we have now, because there is a lot of work to do on exploration. But we need to do the exploration from here, using different technologies related to, I would say, digital treatment of images, etc. So imagine the geological exploration that we need to do here, normally in a mining, I would say, exploration project. But imagine to think in a different way that we need to get the same type of information is what the other company that I mentioned, Aten Engineering, is doing. Is trying to from here to collect that information in order to provide that information to the different companies for them to prioritize what could be the resources that they should go first. If there is any criteria that they can develop, So I think the answer to your question will be find out or will be answered as soon as we get more information on the exploration field, because still I think there is few information on that, but by collecting information, I think we will be able to make a plan, in the long run for not compromising or for not, I would say, just jeopardizing the future generations. So this is my opinion. I don't know.
Thank you.
You're welcome.
Let's thank you, the speaker, again.
Our next speaker is Dr. Yoshiko Fujita. She's a staff scientist at Idaho National Laboratory and a member of the US DOE Critical Materials Institute.
All right, well, thank you for sticking around. We're going to come back down to earth, and actually, we're going to talk about sewage treatment, among other things. So, let's see. Specifically, we're going to talk about some rare earth separation wastes and their possible impacts on wastewater treatment microorganisms. And this is work done, again, for the Critical Materials Institute, which many of you heard about earlier, and with colleagues from the Idaho National Lab, and also a very talented undergraduate student who did many of the experiments during a 10-week internship. That's Elizabeth Rupp. So, as Tom talked about, the Critical Materials Institute is a DOE multi-institution virtual institute where we're looking at trying to diversify supply of critical materials, develop substitutes, and develop reuse and recycling to positively impact supply chains of critical materials. And we're trying to do so rapidly, sustainably, and economically. And that's really the focus of the fourth focus area that Tom mentioned, what he called the cross-cutting research focus area. And that's what this research that I'm going to talk to you about is in. So specifically in this project, we're looking at wastes from critical material production with an eye toward being anticipatory. That is, as new processes, new technologies are developed in the Critical Materials Institute, can we think ahead of time about what the environmental impacts of waste generated by those processes, what those impacts might be and how we might dispose of these wastes. So specifically, we're looking at what I'm going to talk about as waste that might be discharged to a sewer after pretreatment, because often wastes are either disposed or treated on site at mineral processing sites, or at an industrial facility, they might be discharged to sewers after pretreatment. And the reason that we want to think about this is that as if a waste impairs the ability of a sewage treatment plant to do its job, which is to treat waste so that it meets permit limits and can be discharged, that's a really big problem, and a wastewater treatment facility will not accept such wastes. So one of the critical materials that we've heard a lot about today are the rare earth elements. The rare earth elements, I think, as many of us know and we've been talking about, are very important for a lot of modern communication and communication technologies and clean energy technologies, which is really the focus of the Critical Materials Institute. Rare earth element production, again, as we've talked about, is largely concentrated today in a few countries around the world. And in the U.S., we only have one operating rare earth mine, and that's in Mountain Pass, California. And there they're mining the mineral bastnasite. It's a rare earth fluorocarbonate, and it's primarily light rare earths. But because all rare earth minerals contain a mix, they contain pretty much the whole series of rare earths, one of the important parts of processing is separations. So in this figure, this is an overview of the processes that were used at Mountain Pass between 2010 and 2015. I think many of you know that Mountain Pass was shut down for a few years, while and then financing was obtained, and it's now running again. But during that earlier period, this is the basic flow sheet that was used. So flotation, leaching, acoustic crack, impurity removal by ion exchange, and then a lot of the lot of the work involved in producing rare earths goes into separations. In fact, I think I've seen that it's estimated that for the cost of rare earth production, about 60% is downstream of the extraction, so the separations and then the final metal production. And so during separations at Mountain Pass, the separations process used is solvent exchange. Solvent extraction. And so they're separating heavy rare earths from light rare earths, and also using solvent extraction to remove impurities, that is the non-target solutes that would also get extracted, removing cerium, and then that last section, the SXD, is solvent extraction for didymium, which is the neodymium and praseodymium combined. But in those separation steps, there can be like 50 to 100 separate solvent extraction steps. It's extremely it's an extremely expensive and complicated process. And so one of the projects within the Critical Materials Institute is actually trying to improve separations. So they're focusing on the solvent extraction, where we're transferring solutes from the aqueous phase to the organic phase. And typically we do this by using a ligand that can complex with the metal and make it just non-charged so that it transfers into the organic phase. And what we're looking for is ligands that are selective for rare earth elements. Again, as I mentioned, this is a simplified picture of the separations. So there are many steps, many separate steps within it's a continuous process. And there are many extraction steps, many scrub steps, strip, and so on. But what we're looking at is the aqueous stream that's left over at the end. So this aqueous stream, presumably we've removed as much rare earth as we can, but there will be some residual organics that are left in it. And so we're looking at that, raffinate, it's called. So one of the projects in CMI is actually evaluating diglycol amides as ligands for separation. The idea being that using these neutral separation ligands can reduce acid and base usage. And also some of these DGAs, we believe, are better actually at separating light rare earth elements than some of the conventional ligands. One of ones that's shown here is PC88A. So this diglycol amide, TODGA, tetraoctyl diglycol amide, is the most well-known DGA. It's also been looked at for actinide separation. And so within CMI, Kevin Lyon, who is one of the co-authors on this presentation, is leading a project where they're testing different DGA structures where they've changed the alkyl groups to see if they can improve separations. And what we're interested in is what might these new DGA structures, how might they affect wastewater treatment? So one of the functions of wastewater treatment is nitrogen removal. So we decided that, and it's one of the most easily upset wastewater treatment functions, because organisms that oxidize ammonia are actually quite sensitive to pollutants. This is well known from many other studies, to metals and organic pollutants. So in a wastewater treatment plant, biological nitrogen removal generally starts with ammonia oxidation, and then to nitrite, and then nitrite oxidation to nitrate. These are done by, well, actually, sometimes, generally we think of them as two separate sets of organisms, but recently there have been some organisms found that seem to be capable of both steps. And then subsequently, the nitrate is removed by other organisms. But again, there's been some new exciting research that shows that there are some organisms that seem to be able to do the reduction as well. But in any case, that seems to occur under special conditions, so you need to get the environmental conditions just right. So, and then as I said before, because these organisms are so sensitive and they're also quite slow-growing organisms, if nitrification is impaired, it's a problem because it takes a long time for treatment plants to recover. So we started looking at a model nitrifying bacterium, Nitrosomonas europaea. It's the most well-studied ammonia oxidizing bacterium. The red image is actually just it's a microscope image of the cells that have been stained with a fluorescent dye. It's the bright red spots, well, yeah, are the microbes, and then the flocks behind it are it can be organic material, or actually in this case it might actually be some precipitates that they're in. So it's a pretty simple setup that we're using. We're growing these microorganisms, and then we test them. If we want to test a particular pollutant or substrate, we add that, and then we measure changes in nitrite production. So that's the product of ammonia oxidation, and we compare that to the control. And we're doing these in batch flasks in the lab in triplicate. And that image is of the pink tubes. We're measuring nitrite using a colorimetric assay. So this is the results of an experiment where over time on the x-axis we're measuring nitrite production, and in the blue is the control system. So that's where nothing is added. And then we see that when we have neodymium at 33 micromolar, we don't actually see any change in ammonia oxidation, suggesting that the organisms are unaffected. However, in the case where we have neodymium complexed with tadga, and the tadga, the complex for a lanthanide with tadga is shown in the lower right. That's an example for europium. But the point is that for each neodymium, we have 3 tadga molecules. So the tadga is at a concentration of 100 micromolar. And what we see is that when that is provided, it does seem to be inhibitory to the organisms. So that suggests to us that maybe we need to be looking at these organic phase residuals, and we're not really so concerned about the metals by themselves. So tadga is used, so that's the ligand, so that has to be used with an organic solvent because we are trying to extract into an organic solvent. And the one that is often used is known as isopar-L. It's a mix of isoalkanes. And we also often use what's called a phase modifier. And so this is a compound that's used to help the separation of the aqueous and the organic phases. And in this case, what Kevin's been using is called XL13, and again, it's a mix of isoalcohols. So here we're looking at isopar-L on its own, for example. So that's in the green, and we compare that to the control in blue. And obviously there's some variability, but on its own, it does not seem to be inhibitory. We've done this experiment multiple times, and that's consistent with what we see. Again, the tadga in the purple does seem to be inhibitory, and in this case, Kevin gave it to us combined already with the isopar-L and the XL13 because that's the way he uses it. That seems to be inhibitory, and then the XL13 on its own appears to be problematic. So maybe really the issue is the XL13. Then we've, as I said, one of the points of Kevin's project is actually to look at new DGAs for separation. So working with scientists at Oak Ridge National Lab, and they developed some new structures for DGAs that they. So I'm not going to tell you what the structure is, but I'll say one is called LDGA and the other one is called LDGA2. What we found was that the LDGA and TODGA seem to be quite similar to each other with respect to their impacts on ammonia oxidation. So that's the purple and the red symbols. But the LDGA2, that structure is actually far more inhibitory. We really get very little nitrite production. And so this suggests to us that even though these structures are actually relatively similar to each other, the chemical structures, there is something that's different enough that it seems to have make a big difference to the microorganisms. And again, we can also see these effects on cell growth. So these are cell numbers per mil or per milliliter, and these are done by, you take a sample and you fluorescently stain the cell and you count them, cells, and you count them under the microscope. So on the far left, the inoculum means this is what we start with at the beginning of the experiment. And then after, I believe it's 72 hours, in the second bar is the control system. You can see that the number of cells has increased because the cells are growing. They gain energy from ammonia oxidation. And then you see the bars for LDGA and for TODGA are actually pretty similar to the control, maybe a little bit lower. But is definitely inhibitory. So we seem to be killing the cells or keeping them from growing for sure. So that's actually all the data that I'm going to show here today. But what we've seen with these experiments and also some other ones that we've done with other types of organic complexants is that we think that the organic residuals and raffinates are more likely to be problematic for nitrogen than rare earths. And we've actually looked at a number of other rare earths, and we've seen similar results to what I showed you today for neodymium. That different DGA structures have different potential toxicities. And we've also looked at some other ones, again, that I haven't shown you today. But again, yeah, we see that changing the alkyl structure affects the toxicity. And so what we'd like to think of for our project, our role is to provide this feedback to the people developing the technology so that they take this into account as they evaluate new ligands. You know, they might find that two of them are great, they're both really good, they're an improvement, but if one is more toxic than the other, let's choose the one that's less toxic to go further with in terms of developing flow sheets. And again, yeah, the other, not just the separation agents, but the other organic phase components, and by that I mean the solvents, or especially in what we've seen is the XL13, the phase modifier, should be considered as well. So we'd like to thank the DOE Office of Science SULI internship program. They funded Elizabeth Rupp's participation in this research, and she really did quite a lot in her 10 weeks. And we'd also like to thank the Critical Materials Institute for its funding. So any questions? I'd be happy to answer them. Sure. I'm sorry, do what? Do the molecules have any surfactants? Surfactants. Yeah, you know, good. Yeah. Uh-huh. Yeah. That's true. Mm-hmm. Yeah, it could be, yeah, it could, I'm trying to remember it. Well, yeah, I couldn't show you the structure, so now I can't remember what I've seen of the structure. But I think it may have to do with alkyl chain length and also branching. Mhm. Yes.
Denitrifier bacteria?
No, we have not in not in pure culture experiments. We actually, we have a project partner at the Colorado School of Mines, and they're actually looking at activated sludge reactors. So that includes a mix of organisms that would include denitrifying organisms. And so we are doing experiments there as well to we look at changes in some of the, in things like changes in nitrate concentration, chemical oxygen demand, and so on. But also we're looking at community, so the microbial community. We can look at, through looking at the genes of the organisms in that system, we can see changes. We have not yet done that with any of these extractants. We have been working with just the rare earths, though, looking at impacts on of just the rare earths on the microbial community composition.
Okay, thank you.
Oh, sure.
Was this experiment done in only a single batch, or did you give those microorganisms time to adapt to the new organic molecules and possibly over time begin their nitrate or their ammonium oxidation activities again?
These were done over a 72-hour batch. So actually, one thing I was looking at is that if you look at the purple line, the Tadga, it actually almost looks like it's starting to catch up. And I've noticed that also on, oops, sorry, I'm going the wrong way. So that's, and in another experiment with the Tadga, that maybe it can't, if we let the experiment go longer, yeah, perhaps the organisms are able to recover from that, or the ones that, or the communities adapted, the populations adapted, and that the ones that are really susceptible die off, and the other ones are growing up.
Thank you.